So we are going to talk about rather more conventional quasiparticles, electronic quasiparticles, and in particular about how they actually die if one heats a metal. Okay. In there. This is largely the PhD work of Andrew Hunter, very talented PhD student, together with Anna Tamai. He was heavily inspired by Antoine Georges and his group, who really pressed us for some time to look at this issue of how quasiparticles behave if one warms up a metal. In the abstract, I promised to talk about strain, but I doubt that I will actually make it to that part. And the strain part was a collaboration with the group of Philip Moll, in particular with Carsten Putzke. So metals at high temperatures, well, there are a handful of metals where resistivity as a function of temperature actually tends to saturate. This is mostly observed in alloys. And the resistivity saturation occurs at the so-called Mottioff-Regel limit, where the mean free passing in classical Boltzmann transport approach is more or less interatomic distances. Now, in most correlated metals, this type of saturation is not observed, and resistivity just tends to keep growing until one can no longer measure it. And this Mottioff-Regel limit is also surpassed at much lower temperatures in general. Now, if the mean free path is so short, the interatomic distance is much shorter than the Fermi wavelengths, clearly a particle-like description doesn't make much sense, so that there should be no quasiparticles. Okay. Now, let me point out that this behavior is fairly general to correlated metals, certainly in pnictides, ruthenides, manganites, and C60. These two graphs are actually from a nice review from Ole Gunnarsson, just to honor the Max Planck Institute and also Ole Gunnarsson, of course. We are going to study the issue in strontium ruthenate, which is one of our favorite materials, but also turns out to be particularly suitable for this purpose. So tetragonal layered perovskite, very two-dimensional, quasi-two-dimensional. It moved into the spotlight in '94 when Yoshio Maeno discovered superconductivity at quite low temperature was the first perovskite oxide beyond cuprates to show superconductivity. Superconducting order parameter was long believed to be spin triplet, P-wave superconductivity, but this was disproved over the last 5 years or so, and I think is again a wide open issue. But we are just going to look at the normal state. One attractive characteristic for us is that it's a nice liquid at low temperature with a really textbook T-square resistivity. If one warms up, especially the C-axis resistivity, there's a funny thing. It turns from metallic at low temperature to weakly insulating or semiconducting at higher temperature, but no such thing is observed in the in-plane resistivity, which actually just keeps on growing, and it grows well beyond any incarnation of the Mottioff-Regel limit. It also turns almost completely linear at high temperature. Okay, good. Now, just a few words to introduce the electronic structure, which will be some importance for the talk. So it's a multi-orbital system. We have 4 electrons in 3 T2G orbitals. They make 3 Fermi surface sheets. 2 belong mostly to these out-of-plane orbitals, and 1, the so-called gamma sheet, derives largely from the in-plane orbital. This is the first time this was successfully measured by ARPES, Andrea Damascelli back in Stanford. This is more recent laser ARPES data, which has a bit more precision, and that then actually turns out to be quite important for us, for this purpose of this talk, mostly to define a so-called bare Hamiltonian, which will then allow us to look at self-energies. And the first thing that we learned is that if you look at a particular direction, momentum space, slightly off the diagonal, here the bands would actually be degenerate without spin orbit. And this degeneracy is lifted by spin orbit. And so this degeneracy lifting gives us a nice measure of spin orbit coupling. And what you find is that it's about twice the value predicted by DFT. And that's really a correlation effect. We call it enhanced spin orbit, but it's really the off-diagonal elements of the self-energy tensor, which are basically frequency independent. So they look like spin orbit. Now, the second thing is the behavior of the self-energy. And if you do a self-energy analysis along the Fermi surfaces, these two sheets here, we get for the real part of the self-energy kind of a fan that spans quite a wide range. So it looks like a momentum depends to the self-energy, but this momentum depends actually tracks the orbital content of the band. So you do a transformation from a band basis into an orbital basis. This complexity nicely collapses on two different curves, one for the more strongly correlated in-plane orbital, the dxy, and one for the other two orbitals. This is also in fair agreement with DMFT self-energies. Now, what is important for us here is that this means that self-energies are largely local, so there should be no momentum depends to them. Now, what we are interested in this talk is what happens if you go out of this tiny Fermi liquid phase here and you approach, well, not quite the T-linear regime here, but at least higher resistivities towards this Mott-Joffe-Bregel limit. What happens to the fermionic quasiparticles? And if I have time, I will also show something on strain where non-Fermi liquid behavior goes down to very low temperatures. Okay, quasiparticles are defined by their residue, so coherent weight and the weuse. Normally, these two things these two expressions are used synonymous, although at increasingly high temperature, it's not so clear how one should actually even define the weight. So a more rigorous definition comes from the real part of the self-energy here. And if the self-energy has no momentum dependence, then the quasiparticle residue derived like this has no momentum dependence, and it corresponds very simply to the renormalization of the Fermi velocity or the effective masses as you want. And this is something, at least as soon as one has a bare Hamiltonian that is reliable, can be very nicely measured by ARPES. Now, this problem has been studied by many groups before in experiment, and the findings are actually very, very consistent. This is work from the Peter Johnson group, also on strontium rusinate. And you see if you warm up at a particular momentum position, it looks like these quasiparticle band peaks, they just decay. So it looks like said the quasiparticle residue will go to zero. And that was also the conclusion from the paper here. This is not just strontium rusinate, very similar behavior was observed in cobaltates, iron arsenides, and here more recent work on the surface states of strontium rusinate. Looks all very consistent. Whatever you look at, it always looks like SAD, for instance, here, seems to go to zero, and it seems to go to zero well below the Mott-Joffe-Bregel limit. Okay. Now, this also happens to be the behavior of the half-filled Hubbard model we learned here. Doesn't seem terribly well documented in the literature. So quite old DMFT calculations, a half-filled Hubbard model below the critical use. So we have a metal, and at low temperature, we have a coherent quasiparticle peak. And if you warm up, that quasiparticle peak shrinks, and eventually that goes basically to zero. Now in resistivity, let's focus on the black curve here. actually there are two curves. One is theory and the other is an experiment on an organic salt. This corresponds to a Fermi liquid-like resistivity at low temperature, where you have nice quasiparticles. Then a bad metal, where resistivity surpasses the Mott-Joffe-Regel limit by quite a margin. And then at high temperature, where Z is basically zero, the system turns semi-conducting. Okay. Good. Now, this is intriguingly similar to the C-axis resistivity in strontium leucinate, but I think that's probably a coincidence, because if Z goes to zero, one would expect the in-plane resistivity as well to turn semiconducting, and that's very clearly not observed. So this is one of the issues with this picture. The second picture is that if Z goes to zero, the bands become very flat, and nobody has ever reported that. Okay. Now there is another very obvious issue, is that in the MFT, this behavior of Z to zero seems to be very much confined to the half-filled Hubbard model. Already the doped Hubbard model and multiband systems, I think theory universally finds the opposite behavior, that Z should actually go up as one warms up. So what went wrong either with theory or experiment? Okay, and we think after some study of this problem that what went wrong is the analysis of experimental data. This is newer data, part of the data I will be discussing. You see at lower temperature, you have a nice, what we call quasi-particle peak, and at higher temperatures, things are much less obvious. But there's also all this stuff here, which in ARPES we usually don't like to talk about. So really a big chunk of the spectral weight, we don't quite know where it comes from. So if you do any type of analysis, you say, okay, let's take a background, and we say, this is the quasi-particle, this is some background that we ignore. And if you do that, well, Z seems to go to zero. Now, I can sketch also a very different quasi-particle more in this way, and then Z doesn't go to zero at all. It could well be constant or go up or down, who knows? So clearly spectral weights are not such an easy thing in ARPES. So here is our data from low temperature in the Fermi liquid phase up to quite high temperature, about 250 Kelvin. And the first thing that you see is that, well, things become broader, but nothing drastically ever happens. So quasiparticles don't just disappear sharply. They certainly do not disappear as one leaves the Fermi liquid regime at around 25 Kelvin. Also at the C-axis metal insulator transition, nothing really happens as one goes across here. Things just become gradually more broad, and certainly the bands don't go perfectly flat as one would expect for Z to zero. So how do we analyze that? Well, instead of spectral weights, what we look at is the dispersion, because that is also linked to Z via the self-energy. Okay. So we take what is called momentum distribution curves or horizontal cuts here. You get nice peaks. You can fit the position of these peaks. And now if it really is the case that Z actually increases as we heat up, then we ought to see something like that, a relatively flat, low temperature quasi-particle band that becomes steeper as we warm up. Okay, so we do this type of fits for all temperatures. And the first surprise is if we do this at the Fermi level, that actually KF is not quite temperature independent, but there is a certain weak, but definitely real, or we think real temperature depends to the Fermi surface. Okay. Now we do the same thing at a lower energy down here, and we get quite a bit stronger temperature depends in the opposite direction. And now if you have these 4 points here, then the dispersion, well, if you take a parabolic band, the dispersion is completely defined, and you can just calculate it. First, let me come back to this cartoon. So that the picture is almost as what I showed before. The bands really, they become steeper as we warm up, but not quite in the simplest way. There is also some movement of the Fermi surface. So the bands, they deflate a bit. Okay, now I said we simply make the assumption of a parabolic band, and then from these 4 points we can calculate the dispersion. We can compare to the bare Hamiltonian, and we can calculate very easily Z, the quasi-particle residue, and this is what we find here for the gamma band, and for the beta band. This is mostly out of plane orbital, mostly in plane, and we find indeed that Z derived in this way from experiment goes actually up with temperature and not down, as was almost universally claimed from experiment before. The 2 lines down here, these are DMFT calculations. The dashed is actually the proper DMFT Z, which you see tracks our temperature dependence, but is lower in general. We are not yet quite sure to what extent that's a problem of DMFT or of our analysis. Okay, and the green is just a sanity check. We actually took DMFT spectral function, broadened them with an energy resolution, and then redid the experimental analysis to look for the relevance of artifacts. And well, you don't get quite the same as the proper Z, but qualitatively, this is all right. Okay, so you can also see the main effects that are going on here very directly in the DMFT self-energy. So first, the slope of the real part becomes lower and lower as you warm up. That means the bands unrenormalize at higher temperatures. And second is the real part becomes finite at 0 frequency. This is the shift of the Fermi wave vector, or the deflation of the Fermi surfaces. It's actually interesting to know that both orbitals, both bands, the beta and the gamma band, deflate with increasing temperature. So it's not an interorbital charge transfer. Okay. Now we also tried to look, or we looked at the imaginary part of the self-energy. And this, if you do just this one-dimensional analysis that ARPES people usually do, is a really tricky business. Because the energy resolution in ARPES leads to an effective momentum resolution by the dispersion relation. But it turns actually out that close to the chemical potential, that effective momentum resolution becomes temperature dependent. So it's a real mess to get temperature dependent line widths. That's why we restricted this 1D analysis to an energy of 10 millivolts, sufficiently far from the Fermi level. And we find, if we compute the imaginary part of the self-energy, that it goes up really quite strongly with a certain orbital differentiation, and again in overall fair agreement with DMFT. Now we eventually did push the analysis a bit further, because what you really would like to know is scattering rates at the Fermi surface. And for this, you have to do a 2D analysis. So you have to fit the entire image plots, and you have to take care of the experimental resolution. But in 2D, this is very straightforward to do. It can be just a 2D convolution. And like this, we can get quasi-particle scattering rates. This is for the gamma band here. And what you find is that, well, quasi-particles, they really broaden very, very strongly with a multiple of the rate, of the Planckian rate KBT. So this is very, very strongly super Planckian scattering in strontium bruceinate. DMFT quasi-particle line widths computed in, I think, the correct way are slightly below, and we believe that at least part of this difference is electron phonon scattering. Now, some of you might probably have wondered why what happens to electron phonon. The resistivity is very linear at high T, which is typical of electron phonon. And so far, I've interpreted everything as purely electronic correlations. There has been one recent study that combines DMFT calculations with electron phonon scattering. And what they find is the dashed one here is just DMFT, quasiparticle line width, and the solid one together with electron phonon. That electron phonon scattering, of course, is there, but it's a relatively moderate correction to the electronic correlations. Direct comparison is there is a factor of 2 in between the two. Unfortunately, they plotted by mistake that the half-width of the quasiparticle, but that's probably going to be corrected for the published version. From this quasiparticle scattering rates, you can now also calculate quite straightforwardly resistivity as a cross-check. And we did that here using kind of the simple Boltzmann-like transport with isotropic Fermi surface sheets, which is a somewhat crude approximation. But that's what all the transport people do. And they usually go the other way around. They measure resistivity and then they calculate scattering times. So we can go the other way around. And the blue is this resistivity is calculated from our scattering rates, and the dashed is a direct experiment, and this actually works out very nicely. So this all looks so far fairly consistent. So the quasiparticle weights actually increase with increasing temperature, but quasiparticles broaden excessively. Now, what about spectral weights, which caused so much confusion in the past? So the first thing we did, we looked at this with kind of an experimentalist approach to DMFT. These are our DMFT spectra here for different temperatures. And actually the different peaks, these are the three bands of strontium rusinate. And then we tried to extract some kind of coherent spectral weight, which we did by a first order Taylor expansion of the self energy that gives you a spectral function that you can fit to this, and you get the green shaded part. And this all works works out fine. Actually, this green shaded coherent quasiparticle weight does increase with temperature, and it's plotted in green here, and it tracks more or less the proper quasiparticle residue calculated from the self energies. Okay, now what about the experimental spectra? And it's quite clear that really the big problem here is the so-called background. And we thought that probably the most honest thing to do is, if you want to look at the temperature bands of a spectrum here, the quasiparticle is just a bit on the occupied side. We take a spectrum a bit on the side here at the symmetry point where there is no quasiparticle band as background, and we just subtract the red one from the black one. The black one looks something like that. What we actually do is we fit some polynomial to it and then move on to the subtraction. And if you do that, even at relatively high temperature, 150 Kelvin, there is still a bit something left. And because we did this experiment quite systematically, we can actually do that for all the temperatures in exactly the same way without any factors in between. And these are the spectra that we obtain like this. Well, not very much left, but perhaps something. And now comparison is, well, so we cannot fit the same function to the data. Somehow the function is too temperamental and it doesn't like that. But what we can do, of course, is overplot the calculation on the data. And for that, we first have to convolve it with an energy resolution. So we mistreat it a bit to resemble the experiment more, but that's quite an honest thing to do. And you see that without any additional scaling factors, so this works out actually very, very nicely. So there is probably no mystery here, and it really is the case that quasiparticle residue, at least in this Hund metal, goes up as one warms up. Okay. So what is clear is that quasi-particle-like excitations extend well beyond Fermi liquid regime, unless one takes a very orthodox definition. Scattering rates are really strong in strontium rutheniate. Okay, and finally, also the Fermi surface is not just constant, but becomes temperature dependent. Okay, I think in the interest of time, I should stop here, and I thank you for your attention.